In this video, we're going to look at predicting using a linear regression. We have the Toluca company data, where a company produces parts, and for varying lot sizes of those parts, we see that the work hours increases with increasing lot size. The goal is to predict how many work hours it's going to take for a certain lot size. After I get my regression, I get my slope and my intercept, and I can put them into a linear model. If I want to predict the number of work hours for a particular lot size, like 75, I can just plug 75 in to the equation for the linear model and get a point estimate of my prediction. So when the lot size is 75, we're predicting that the manufacturing is going to take about 330 hours. In R, if we've done our model in R, we can use the predict function to get that point estimate. LM fit is the name of the model that you fit, and then this new data has to be in a data frame, and you have to use the same variable name for X that you used to name your new data X. So for the Toluca model, you can see that I did the Toluca data set, and then I called it Toluca model, and Y is work hours, and X is lot size. And then when I go to predict, I put that model name in, I put my new data frame, and my lot size, it's the same variable name as I used for X before, is 75, and I get my point estimate. You'll recall that when we first started talking about linear models, I gave you two forms of the linear model. One with a yi hat, and one with this expectation of y given x is some value. So we're going to talk a little bit about the distinction between these two. In the first one, we're talking about an individual predicted value. In the second one, we're talking about the average of the y's for a given value of x. We'll talk about that one first. So this is going to be making a confidence interval for the mean of y when x is some value x, and that's a little xk. When we're going to make a confidence interval, we're just going to use a normal confidence interval form. So you remember we do the predictor plus or minus some multiplier, usually like t or z or whatever, and then the standard error of our estimator. So that multiplier is going to be determined by what distribution that test statistic has. So go back always to like when we were doing the normal distribution stuff, because I think that if we just refer back to that, it's easier to realize what's happening because it's all kind of the same thing over and over again. So you make some assumptions about your x, and then you can see that this statistic is distributed approximately t, and so our multiplier is going to be a t. This guy is really similar, right? So we have our predictor, and we need our standard error of our predictor. This should have a hat on it. There we go. And then we're going to look at some conditions. So you'll recall our conditions. I put them on this slide over here. Just give you a second to remember that we have to have the correct mean model, and we have to have a good functional form, and we have to have independence and constant variance. Now, assumption 5 about the normal distribution. We either need for these intervals, we need the 1 through 4, but 5, we either need it to be normally distributed, those residuals, or we need our n to be large. So when we have conditions 1 through 4 and our residuals are normal or our n is large, then we use this guy for standard error. You can always look it up in the book, okay? You don't need to like memorize this formula or anything. And we have this guy is distributed t, and if it's got two parameters, so it's actually like n minus P, but because we're only using beta naught and beta 1 here, it's a n minus 2. So that's going to be our multiplier. You won't actually have to do the calculation by hand because we're just going to use R. And using that same predict statement, we can now add this other bit, this where it says interval equals confidence, or you can just shorten it by doing interval equals C, and it will give you a confidence interval as well as the point estimate. So you can see here the same thing I did before where I've got my 75. Now I have my point estimate, the 330, and I have a lower and an upper confidence bound. In this, if you don't put any confidence level, it will give you 95% by default. If you want to change the confidence level, all you have to do is put level equals and then the new confidence level you want. All right, let's talk about the other one, which is to predict a new observation of Y. So how does this differ from the average? Before we were talking about an interval for the mean. So the mean is going to be along that blue line, and we just want an interval for that average value. A new observation, that has to take into account all of the variability of the data as well, not just the variability of the mean value. So the interval is going to be wider because we're going to need more variability to account for the variability of the actual data, since a single new observation is different than the mean of new observations at that x. So when our conditions 1 through 5 are met, and you'll notice now I actually need them to be normally distributed because I have to take into account how those values are distributed around my point estimate. So when they're met, I have the same multiplier. This is new. Yeah, so let's compare it to the previous one. That one is adding the variability to make my interval wider. So to get a prediction interval, this is what we call it. Instead of a confidence interval, it's called a prediction interval because we're predicting a new value. We just do interval equals P for prediction. And we're going to get a wider interval. So I'm going to sketch it here on the plot so you can see how it is. So here our prediction interval goes from about 227 to 433. So we're saying that our new observation, we think, we're 95% confident that it is going to be in there. If we look at the confidence interval for the mean value, it is much narrower, from 309 to 350. So this one we're saying we are 95% confident that the mean Y for that X is going to be in there.